Throughout the talk, the term group means finite group and the term graph means undirected graph without loops and multiple edges. In the finite group theory, there are a lot of questions of a group recognizability by a certain set of these group parameters up to isomorphism. So let me show some of this and let me give you some definitions at first. Let G be a group. The spectrum omega G is the set of all element orders of G. The prime spectrum pi G is the set of all primes belonging to omega G. A graph gamma G, whose vertex set is equal to pi G and in which two distinct vertices P and Q are adjacent if and only if PQ belongs to omega G, is called the Grunberg Kegel graph of G and is denoted, as you can see on the slide. A group G is recognizable by Grunberg Kegel graph if for every group H the coincidence of their Grunberg Kegel graphs entails that G and H are isomorphic. A group G is called almost recognizable by Grunberg Kegel graph if there is only finite number of pairwise non-isomorphic finite groups with Grunberg Kegel graph like the group G. If G is not almost recognizable, then it's called unrecognizable by Grunberg Kegel graph. If G is a non-abelian simple group, then we say that G is quasi-recognizable by its Grunberg Kegel graph if every group H such that the Grunberg Kegel graph is equal to the Grunberg Kegel graph of G has an unique non-abelian composition factor S, which is isomorphic to G. The study of the recognizability of finite groups by the Grunberg Kegel graph belongs to the modern research, and the special attention attracts to the study of a class of finite groups with a disconnected Grunberg Kegel graph, because this class generalizes the class of finite Frobenius group, which is evident from the well-known Grunberg Kegel structure theorem. So let me remind this theorem. If G is a group with disconnected Grunberg Kegel graph, then one of the following statements holds. From the first, it follows that G is a Frobenius group. From the second, it follows that G is a two-Frobenius group. And from the last, it follows that G is an extension of an nilpotent group by a group A, where the following equality holds. And S is a simple non-abelian group with disconnected Grunberg Kegel graph. As I said earlier, this topic is relevant at the present time. For example, the problem of the structure of a finite group G was studied in two independent studies. Let me remind results that were obtained in these works. In 2011, Kondratiev and Khromtsov have presented a description of the main factors of commutators of finite groups whose Grunberg Kegel graph has exactly 4 vertices and is not connected. In particular, they showed that if G is a finite group whose Grunberg Kegel graph consists of 3 connected components, namely the first component is a clique between 2 and 3, and the second component is a vertex 7 and the third component is a vertex 13, then G is isomorphic to G23. However, in the same year, Zhang, Shi, and Shen have proved that G23 is quasi-recognizable by Grunberg Kegel graph. And now, let me get rid of this contradiction with the help of the main result of this talk. If G is a finite group, the order of the prime spectrum of G is equal to 4. 5 doesn't belong to the prime spectrum of G, and the first connected component consists of 2 and 3, then the prime spectrum of G is equal to the set of 2, 3, 7, and 13, and one of the following condition holds. From the first, it follows that G and G23 are isomorphic. In the second statement, we denoted by O2G the maximal normal to subgroup of G, and then factor G by O2G is isomorphic to PSL 213, and each two-shift factor of G as a factor of G by O2G module is isomorphic to the direct product of several isomorphic copies of one of two irreducible six-dimensional GF4 PSL 213 modules. Each of these statements of the theorem is realized, and as a corollary of this theorem, we can say that groups G23 and PSL 213 are unrecognizable by Grunberg Kegel graph. Let me now talk about the scheme of the proof. A group G is an primary group if and only if the order of pi G is equal to n. So let G is a finite four primary group. The order of G is not divisible by 5, and 2 and 3 belong to the first connected component by 1. Also, let Grunberg Kegel graph of G has 3 connected components. Here we denoted Fg by fitting subgroup. Here we denoted by Fg the fitting subgroup, and it is a unique maximal normal nilpotent subgroup. Since Grunberg Kegel theorem, the factor G by Fg is almost simple, because if the group G were a Frobenius group or a two Frobenius group, then its Grunberg Kegel graph would have to consist of 2 connected components, but we need that Grunberg Kegel graph of group G is connected of 3 connected components. It consists of 3 connected components. As I said earlier, we consider groups whose Grunberg Kegel graph consists of 3 connected components, where 2 and 3 in the first component, and the order of circle is not divisible by 5. The description of 4 primary simple groups based in the results by Zhang, Shi, Shen, and the description of connected components of Grunberg Kegel graph of finite simple groups we can obtain in papers by Williams and Kondratiev. Using these results, we can understand that only 2 groups meet the stated conditions. There are PSL 213 and G23. whose Grunberg Kegel graphs are equal, so the circle belongs to the set of PSL213 and G23. Moreover, by atlas of finite simple groups, we obtain that the factor G by fitting subgroup is a circle. Since odd S is equal to 2, then in general, we have two options what is can be equal to. From the first case, it's equal to circle, and from the second case, this factor G by fitting subgroup is an automorphism group. But the case when the factor G by fitting subgroup is an automorphism group does not fit because the Grunberg Kegel graph contains an edge between 2 and 7 because 14 belongs to the spectrum. By our definitions, we need a Grunberg Kegel graph with 3 connected components with clique of 2 and 3 in the first component, 7 in the second component, and 13 in the third component. So the factor G by fitting group is a circle. After that, using calculations in the gap computer algebra system, and since the fact that the first component consists of clique between 2 and 3, we consider tables of 2 modular and 3 modular characters of G23 and PSL213. Since we know the table of irreducible p-modular Brouwer characters of the circle of a group G, we can apply the lemma formulated on this slide. We have 2 neighboring members of the main series of a group G that are containing in a fitting subgroup. Then their factor is an elementary abelian P group for some prime number P, and it can be considered as an irreducible GFP G modular. Since this fact, the problem of studying the structure of group G is reduced to the problem of describing irreducible GFP G modulus. Thus, the result of the work is the correction of errors in the papers by Kondratyev, Kramtsov, and Zhang Shen. Thank you for your attention.
Thank you so much, Kristina, for your talk, which corrects some previously made errors. Thank you so much. Are there any questions, comments? Yeah, Natasha, please.
I'd like to make a comment about the common situation in this talk. First of all, for mathematician, it's very strangeable to believe in some magic. However, here they have an example of some magic finite simple group, which vanished exactly in 2 papers at the same year. I don't understand the reason, since I have checked carefully. Not one of these papers refers to another. These are 2 completely independent papers, and in both situations, this group vanished in the main results. I cannot understand the reason. Possible it's special situation, but then they have understood that there is a mistake here in a paper by Kondratyev and Kramtsov, and as well as in the paper by his co-authors. I have asked Kristina to check carefully this group, and her results really repairs both papers. this is not just a counterexample, but this really repairs the result by Kondratyev and Kramtsov, and now there is no trouble in this result. So this is all I wanted to tell.
So thank you for your comment for the history. So are there any other questions, comments, suggestions? So maybe I have one stupid question because I'm not familiar with this topic. But you in the main theorem you have some conditions. For example, that pi1 should be equal to 2 or 3. 5 does not belong to, let's say, pi of g, as I understand. Yes, but is it possible to maybe avoid one of these conditions and you maybe you obtain more possibilities? Yes, for the group G. Maybe do you have some examples? For example, if we save all conditions except, for example, that 5 does not belong to pi of G. So
in this talk, first of all, I read the theorem from these works, so I get only example of this theorem.
Yeah, I understand. Natasha, do you want to say something? Yeah.
Yes, really, the statement of the theorem can look rather strangeable. However, the aim of this theorem is to repair the mistake in the paper by Kondratyev and Kramtsov. Really, all the other possibilities have been considered, I believe, correctly. And the possibility then the prime spectrum has exactly 4 prime divisors, and 5 doesn't belong to the prime spectrum, and the first connected component consists of exactly 2 and 3. This was some exceptional case in which there was a mistake, and unfortunately then they checked this paper. There were no detailed proof in the paper by Kondratyev and Kramtsov. There was just a reference to gap.
Yeah, I understand.
So it was necessary to check carefully exactly this case. So it was a reason then I have asked Kristina to consider exactly this case.